Welcome, ladies and gentlemen, Physics Academic, to the Simpkins Physics Corner. Today's topic is motion. Hey, before you start, go to Canvas, download the note sheet for pages 2 and 3. It starts with Week 5 Launch, Intro to 1D Motion. If you have these notes, you can follow along with this lesson. Taking notes, feel free to pause the video. I've been told I talk a little fast, so feel free to pause the video at any time to check out these things. We are going to talk about things that move. So this guy looks like he's moving, and this skateboarder looks like they're moving. But how do you know if an object is moving? Well, we define motion in physics as a change in position over a time period. So if I take a picture of somebody and they're over here, and then I close my eyes, count to 5, and I open them, and now they're over here, and I take another picture, they move from here to here. And if you're not at the same place at some other time later, then that means you must have moved. And so if we want to identify or describe something's motion, we're going to need to know two things. We're going to need to know where it is, and we're going to need to know when it is, position and time. So those are the two factors that we need to know. Let's take a look at some motion maps. All right, motion maps are just basically a series of intervals at equal time intervals. So if you've ever watched the X Games, the Winter Olympics, you've seen these crazy athletes. One of my friends that I used to work with is now a photographer, and she does this kind of stuff. Is you can set your camera to go and take a bunch of pictures really fast all in a row, and then you can stitch them all together. So a motion map is basically that. It's a series of images that takes a picture every so often, and it's going to track the motion of that object as it moves. That's what a motion map is. A particle model is very similar to that, except I can't draw worth a penny. So instead of trying to draw a picture every time, you just replace the object with a dot. And the dot represents where the motion or object is and at what time. Now, the cool thing about that is we usually imply time in that. So imagine setting your camera up to take a picture exactly every 1 second on the second. 1, 2, 3. This is what it might look like if you stitched them all together for this runner. 1, 2, 3, 4. Okay, now I'm going to go over some German folklore here in physics class. Why might you do that, you ask? Well, because Hansel and Gretel are two little German children that were one day skipping through the woods. Now, this is the pre-GPS and cell phone days. So they said, well, how might we find our way home? Well, Germans, I don't know if you know about this, they are known for their precision. My dad's traveled to Europe, and he said the trains in Italy were a nightmare, but the trains in Germany, boom, they were right on time all the time. The Germans are known for their precision. So this little German child, Hansel and Gretel, little Gretel there, has a basket full of bread, and she's like, well, Hansel, all I got to do here is just take a breadcrumb and drop it every 5 seconds on the dot. And as I drop these little breadcrumbs and we walk our way through the woods, if we get lost or if it's starting to get late, we can turn around and follow the breadcrumb trail home. Great plan, right? Except woodland creatures find breadcrumbs absolutely scrumptious. And so what happened was these little German kids, they're skipping along the woods, 1, 2, 3, dropping breadcrumbs at regular intervals. Why? Because they're precise, they're German. She knows, she just has this time ingrained in her. Every 5 seconds, Gretel is dropping a breadcrumb, right? Now, of course, the woodland creatures came along and ate up all of those little breadcrumbs, and they couldn't find their way home. And that's how they got to this house made of candy, which was inhabited by a witch. And then depending on which version you read, either the kids got eaten or the witch got burned up. Depends on if you're the sensitive American version of the German one. Anyway, I digress. What if we came across this trail of breadcrumbs in these woods? What could we imply about the motion of Hansel and Gretel? Let me give you some examples. What if we came across some breadcrumbs that were like this in example number 1? They were spaced very evenly. What would we imply about the way that they were moving? Answer, we would imply that they are moving at a constant rate. How do we know that? Well, we can count on little Gretel for dropping a breadcrumb exactly every 5 seconds. And if the breadcrumbs are spaced evenly, and we know that they were dropped at even amounts of times, then we know that the distance over time was also even or constant. They were moving at a constant speed. Let's think about what this would mean. What if we came across a trail of breadcrumbs and the breadcrumbs started close together, but then they grew further and further apart? Now, Gretel's not slacking. She's still dropping the breadcrumbs every 5 seconds, right? We can count on that German precision. What does that imply about the motion then? Well, if you cover a little bit of distance and then more and then more and then more and then more in the same time, what are you doing? Well, of course, you're speeding up. You're speeding up. So this is constant motion over here. This is speeding up here. Let's see if you can take this all the way to the end. What if we came across these trail of breadcrumbs and they started far apart, but then they got closer and closer and closer and closer? Could we imply from that? We could imply that they were slowing down. Why? Because if we can count on her to drop a breadcrumb every 5 seconds, You know that these breadcrumbs were dropped at an even amount of time, but the distance got shorter and shorter. Why would your distance get shorter? Because you're moving slower. All right, so that's the story of Hansel and Gretel and how it impacts our understanding of the particle models. Let's take a look at another picture here. Just to summarize that, if you have an equal spacing on a motion map or a particle model, that will imply a constant speed. And if you have not equal spacing, that will imply a changing speed. Now, when we do this, we have to know where we start and which way we're going. And so we use a coordinate system which tells us where is 0, and it tells us the direction that we're headed. Which way is positive, which way is negative. All right? So the origin is defined as the 0 point. So in these pictures, origin, origin, origin. The position, of course, is the distance and direction from the object. All right, what does that mean? Well, let's look at this last picture. If my tree is my reference point, or my starting point is my reference point, I might say that my x0, my initial position over here, was -5 meters. Why negative? Because it's to the left of our starting point. Okay, so that's kind of what we're getting at with the position. It tells us how far away we are from the origin and in which direction. Okay, and now if we're positive, usually some of the terms that we will use along with positive are right or east or north or forwards. Those are some examples of positive positions. And then, of course, negative positions would be things like the words left, west, south, backwards, down, okay? So any of those traditional directions, if you consider in math class how you have like your x-y axis, right? Basically, in math class, anything that's up is positive, and anything to the right is positive, and then anything that's to the left is negative, and anything to the that's down is negative. So you can think about it like the math class thing when we set up our coordinate system as well. Now, when we are talking about the way things move, and we're talking about different types of descriptions of motion, we need to know the difference between vectors and scalars. What is a vector? What is a scalar? Well, both vectors and scalars have magnitude, and people get confused by this word. All that magnitude means is the number associated with something. So I'll give you an example of that here in just a minute. But scalars have only magnitude. And so some examples of that. If I took my temperature, right? My temperature, well, hopefully I'd read 98.6, right? Your average temperature for the human body. Okay? That doesn't have a direction. It's not 98.6 degrees north. All right, that'd be silly, right? My mass, if I stepped on a scale, right, I'd probably weigh like about $160 or so. So if I had 165 pounds southeast, that just sounds weird, all right? These things, if you step on a scale, you get a scalar quantity, all right? And what happens when you step on a scale? You get a quantity without direction. Now, it turns out that distance and speed are also scalars. Speed is a scalar, all right, because they both start with S there, and because they only have magnitude. But vectors have magnitude and direction. Oh, yeah, if you remember that guy from Despicable Me. Some examples of that would be like an airplane's course. If you were flying somewhere and the pilot got on and was like, shh, we are going about 150 miles an hour, and he didn't tell you which way you were going, you might be concerned that you were on the wrong flight. So the airplane's course would have a magnitude. The magnitude there would be 150 miles per hour. The direction would be something like maybe north-northeast, or I don't know, whatever. Okay, so magnitude, don't get confused by the term. It just means what number are we talking about, how much of it, right? And then the direction is which way we're going. Now, it turns out that displacement and velocity are vector quantities. Look at this. Speed is a scalar. Velocity is a vector. It's a great way to remember that. But make sure you're not doing that in class, spraying your spit all over the place. When we talk about time intervals, time is also a scalar because it doesn't have direction. It only goes one way, right? And if you ever see this symbol right here, this delta symbol, it's a Greek symbol delta. It means change in. All right, so like delta t would mean change in time. And whenever you have a change in something, it's because you started with an initial amount, some initial amount, and then you ended with some final amount. Well, if you want to know the difference between those two, you just subtract them. So you would take t final minus t initial. Let me give you an example. Let's say Mr. Simpkins was tracking some motion, and the object started when his watch said 3 seconds, and the object stopped moving when it said 12 seconds. How long was the object moving for? Well, that's an easy problem. You would just take the final time minus the initial time, and the change in time, or the amount of time the object was moving, would be the difference between those two, 9 seconds. When we talk about distance, distance is a scalar, as we mentioned. It's how far the object has gone, and everything counts, okay? So I want you to remember that if you take a step, that counts for distance. But displacement is a little bit different. Displacement is how far you are from where you started. It's the change in position from the initial to the final position, okay? So we're going to go over an example here of the difference between those two. They're both measured in meters, but one has direction, which is displacement, it's a vector quantity, and the other is just a scalar, so it just has magnitude. Look at this picture. It's on your notes here. You can do it with me here. Look at this picture. Let's go ahead and talk about how we would get the distance traveled. Well, remember we said distance, every step counts. So how many steps did we take? Well, we did 10, 4, 8, 6, 3, and 2. Everything counts because if you're moving, you're covering a distance. So let's see, that would be 14, 14 plus 8. Let's do this really fast here, would be 22. Chuck another, here's a 5, here's an 11. 11 plus 20, all right, it looks like we go 33 meters for distance. I just added all those up one at a time. How about displacement though? You see, displacement is defined as how far we are from where we started to where we finished. Now, if you're a pirate, X marks the spot, and if you're a physicist, X marks the position. Okay, so that's why we use X for that. And displacement, which is how far are we from displace to that place. Displacement, displace, that place. I love it, it's great. So how far did we go from here all the way over to here? Well, let's see. All right, you notice that straight line distance that I drew. Well, that would be made up of 10. This part is 8, and this part is 3. And if I added those together, I would get 21 meters. Don't forget displacement has direction, so I might say something like to the right. So let's go back here and recap. The distance is how far you went. Every step counts. Displacement is a vector that tells you how far you ended up from where you started and in what direction. So that's why this one would be 21 meters to the right. Let's wrap this up at the bottom of your notes. Try this out with me. I want you to pause the video right now. Try to represent these 4 things with a particle model, and then unpause the video and check your answers. So here we go. Okay, so a car driving with cruise control, right? Cruise control means you're going at the same speed. My piece of junk 2010 Honda Civic DX does not have cruise control, and I'm totally not triggered by that every time I talk about it. Sitting rabbit gets startled and runs away. So it's sitting there, it's not moving very fast, and then all of a sudden the rabbit takes off and goes really fast. Remember when the dots increase in their separation as we go on? That means we're speeding up. A sled slides to a stop at the bottom of the hill. So it's going, it's going, it's going, it's going, and then it stops. All right? And then finally, you walk slowly for 5 seconds. So 1, 2, 3, 4, 5. And then walk quickly for 5 seconds. Yeet! 1, 2, 3, 4, 5. All right? So if you drew dot diagrams like that on the bottom, you're tracking with this dot diagram thing. All right. So from this episode of the Simpkins Physics Corner, what I want you to take away are our definitions for what it means to move. If you are moving, you are changing your position in a certain amount of time. We have a couple of different terms that you want to make yourself familiar with in these notes, which are scalars and vectors. Scalars have magnitude, vectors have magnitude and direction, and we gave some examples of those, like distance versus displacement and speed versus velocity. In our next lesson, we'll get a little bit more into speed and velocity, and we're going to start to look at graphs for how we can describe motion of objects. Until next time, make sure you like, sub, and hit the little notification bell so you get the next hottest episodes of the Simpkins Physics Corner. This is Mr. Simpkins from the Simpkins Physics Corner. Until next time.